Welcome TSGC representatives and honored guests. My name is Kyle Randall. Team Calypso is excited to present our project with you all today. We are proposing our solution to the Micro-G Next Design Challenge, a spacesuit attachment quick release system. So, without further ado, we'll give Xavier Shockney our attention.
Thank you, Kyle. To give you a little bit more details on the background of our research and design, I'm going to tell you about NASA's plan to return to the moon by 2024 through the Artemis mission. On these missions, they'll be carrying tools on their new XEMU spacesuit. They will have a belt attached to the XEMU, which they will store their tools on, and they need a receptacle system to do so. The current system is not up to the task because the lunar surface presents unique challenges for design. This is where the NASA Micro-G Next program comes in. This allows undergraduate students to further aerospace engineering by presenting a design for a current aerospace problem to NASA. For the research behind our design, we had to look into why we had to create a new receptacle design. The lunar dust properties on the lunar surface are that it is abrasive, magnetic, and adhesive. These three properties combine to make a very difficult and hazardous material to work in because of its wearing down of seals and destruction of mechanical equipment. As you can see, there's an ISS-EMU utility belt in sight there, which you can see presents mobility problems to astronauts as well as visibility. The current system is a bayonet and probe system, which uses a bayonet attached to the tool, which then slots into a receptacle attached to the belt of the astronaut. The current tool is not dust tolerant because the receptacle is susceptible to getting dust into the receptacle and preventing the bayonet from inserting into the tool. It's also difficult to handle because of its small size. So Micro-G provided us our specific design criteria, which included a need for dust tolerance because of the lunar surface. It needs to support at least 15 pounds of weight for any tool that's going to be used on the lunar mission. It must be operable outside of the direct line of sight of the astronaut. It must be operable with one hand, giving the other astronaut a free hand to do anything else. It must be safe by not having pinch points, entrapments for fingers, and other sharp edges or disasters for safety. It must be in a volume of 4x4 or 3 or smaller, and it must be a total weight of less than 2 pounds. So we took all these criteria and we turned it into design goals to guide our preliminary designs throughout the semester. We use the engineering design process to follow through with these goals by imagining, creating, and testing, and then improving on the goals that we created for the designs we came up with. To tell you a little bit more about the preliminary designs that we came up with over the semester, I'll hand it off to Min, who can tell you more about them.
Thank you, Xavier. After the announcement of the challenge, the team proceeded to coming up with ideas that will help combat with the problems presented by the challenge. The first idea that we came up with is called plug-in. Plug-in is operated by pushing down either sides of the exposed flanges that will allow room for the niche when it's connected to piece 2. The main prongs are included to ensure that the two pieces will stay in place should any sudden movement occur. Although plug-in has locking features that will ensure the connection of the two pieces, it doesn't have the tactile features that the team tries to aim for. In addition, there's a possibility of the flanges getting jammed by lunar dust. The next design that we came up with is called clip-in. Clip-in is inspired by the mechanism and structure of the clip of a pen. It's operated by simply inserting the clip into the receptacle. At the same time, the center will retreat, allowing room for the clip to be inserted in. The center will then go back to its initial position, thus locking and connecting the two pieces together. Clip-in's locking feature isn't promising because the center doesn't have enough room for it to retract, therefore it doesn't work the way that the team intended it to work. In addition, it doesn't address the problem of dust tolerance quite well. Now, this is the last preliminary design that we came up with. Is called I.S.L.E, which stands for Interlocking System for Lunar Exploration. This design is more complex compared to the other designs. I.S.L.E includes a secondary locking system and an indicator. John will help us explain the details of I.S.L.E. With all the designs that we came up with in addition to the current bayonet system, we've compiled them all together compare them using the build chart. Compared to the bayonet system, I.S.L.E, despite being more complex, it's way more advanced in terms of dust tolerance, tactility, durability, and safety. Therefore, the team decided to move forward with I.S.L.E. Now I will refer to John so that he'll better explain the details and the mechanism of I.S.L.E to help us understand our proposed design.
Thank you, Man. So let's take a closer look at the I.S.L.E design. The system is composed of two parts, the first part being the XEMU receptacle, which will be attached to the astronaut's belt, and we refer to it as the cradle. And the second will be the EVA attachment, which will be attached to the astronaut's tool. The system features an open design which allows dust to flow freely through the receptacle, thereby making the system dust tolerant. Per the requirements of the Micro-G challenge for a snug-fitting design, 2 detent pins which are incorporated in the bracket of the XEMU piece, which cause a constant tension on the knob when it's inserted, not allowing it to freely be slipped out. In addition to the detent pins, the team has included a clip that can be folded over the knob and locked via a slit. The system includes a tactile or visual system that firstly allows the mission control to see the completion of the system, but also should the astronaut run their finger over the top of the design, they can know that the knob is fully seated within the cradle's receptacle. Here's a 360 view of the I.S.L.E. Here we see the knob being extracted from the receptacle. Now we see as the knob is inserted into the receptacle, the extrusion causes the left side of the tab to go down, thereby causing the right to go up, which serves as the visual and tactile system, after which the latch is closed over the system. With that, I'll turn it over to Alma for testing.
Thank you, John. To make sure that the design meets all the requirements given by NASA, the team has 3D printed a model of the design and performed a weight capacity and dust tolerance test. These 2 pictures are from the weight capacity test, which was performed with gloves to simulate the gloves that the astronauts will be wearing during the simulation. The design was able to hold a heavy-duty tool despite its materials, which gives us the confidence that in the future it will hold the weight required by NASA. Following is a video of the dust tolerance test. The team used baking soda to simulate the lunar dust that the design will be exposed to. The system was able to successfully work after being exposed to the baking soda. Going forward, the team will be following a manufacturing plan and will be working with machine shops to get the materials needed to prototype this model. Team Calypso has successfully designed a spacesuit attachment quick release system that meets all the requirements given by NASA. This design has been successfully tested and we will be making iterations according to the observations. Now I will be giving it out to Kyle, who will talk more about our future work.
Thank you, Alma. And now as we consider Team Calypso's future work, we're helped to understand that the manufacturing plan has been set in place, and we also have redesign iterations through the engineering design process that will be constantly made throughout the remaining of this semester. And if selected on Micro-G next, we'll be able to test at the Neutral Buoyancy Laboratory. And then another major component of our project is the outreach events. Cosmic Connection is an educational video our team created for the Harris County Public Library to teach young audience about the solar system and to inspire them about space exploration. The Gulf Coast Intercollegiate Consortium is a research conference where our team presented work on TSGC and Micro-G to inform our peers about NASA opportunities and inspire them to participate in future design challenges. And we plan on doing the same at the Virtual Honors College Research Day. We'd like to move into our acknowledgments and thank Dr. Wong for her advising, as well as TSGC and Micro-G for allowing us undergraduate students to participate in the design challenge to further space exploration. Thank you, and now we open up to questions.